So today, starting with 3, 4, 3 more lessons, and that'll be everything that we'll be covering before your midterm. Okay. So your midterm will cover everything from 1, 2, and 3. Okay, just so you know. Obviously, we're into functions now. Okay. Learned all about that in 3.1. 3.1 talks about functions where you can't have the same x value twice. Learned about that. We learned about the domains of functions, the implied domain of functions. And then we got into linear functions. A linear function is any first degree polynomial that just makes a line. That's why we call it a linear function. You graph plenty of those. Then we got into quadratic functions. That's something of the form x squared. F of x is equal to x squared. Anything of that form. So it's anything of the form with a power of 2, a second degree polynomial. Okay. Now let's learn the rest of them. The only ones we're leaving out till chapter 6. Okay, there's 2 other ones that we're learning about. But this pretty much offers most of them that you're going to see. Okay. Some that you're going to see now and you're never going to see again. Okay. But it is good to know about. So I'm going to try to show you ways, because a lot of your midterm, not a lot, at least 3 questions, is going to be saying this. Hey, consider this function. And I'm going to give you a function, right? It's going to say f of x is equal to something. First off, tell me what the graph looks like. Okay. And remember, by looking at the graph, you can always, no matter how weird the function gets, always look at the leading degree, whatever that first degree, that degree is, that the main degree, the largest degree. Okay. You look at the whatever the degree the polynomial is, and then that should give you an idea. You can go, okay, man, there's a power of 2. I know there's going to be a parabola. I know that. I know there's a parabola. Now, there might be stuff going on in that, but I at least went that far with it. Does that make sense? Okay. So let's look at this first one here. So we have power functions. A power function is a function of the form f of x is equal to ax to the r, where a and r are real numbers. Okay? So no longer you're going to have just x to the power of 2. We'll just pretend a is 1. You may have x to the power of 3, x to the power of 4, x to the power of 5, x to the power of 10. Okay? But there is patterns. There's very distinct patterns. Okay? So look at this first one here before I get down too far. Notice what we have here. X to the power of 1 is a first degree polynomial. There it is right there. You know that creates a line. You've learned that, right? If you also notice, whenever you create a line, notice it goes all the way across all the quadrants, right? Not all the quadrants, but you get what I'm saying. Okay. Notice though, x to the power of 3. Well, notice now we're going to a 3. Well, look what happens. You still, bear with me here, you still have something that does this, but now there's a slight curve to it. Instead of creating a line, we've added just a little bit of a curve. Okay? Well, look what happens to the power of 5. Same curve, a little bit longer around the x-axis. It just gets a little wider. So as that power goes up, that distance right here is going to get wider and wider and wider. So if I gave you like x to the power of 15, you can imagine a line doing this, coming down and just going, and then finally going straight back down again. But if you can base it off going, okay, this has got an odd power, right? Odd powers always make a line. They can start off because power of 1 makes a line. Base it off that. And there's your pattern for that one. Does that kind of help you out a little bit? Okay. What do powers of 2 make? X to the power of 2 makes a what? Oh. What do you think x to the power of 4 is going to make? Go with the same reasoning here. What do you think x to the power of 4? If a power of 2 makes a parabola, what is a power of 4 going to make?
A parabola.
A parabola. How about a power of 8? A parabola. Let me show you.
So the odd powers make those lines,
Yeah,
and then evens make.
parabolas. It's just look what happens on a parabola. With a power of 2, you got a perfect little what? Look, here's the power of 2. And look, this guy just does what we all know. Hey, it comes down and goes straight back up again. But a power of 4, look, it starts to kind of level out for a little bit. Power of 5 is going to level out for a little longer. Now, remember what I said. These are kind of like the base functions. Like x to the power of 5 is going to do this. Okay? If that's all I gave you. I'm not going to do that. What's going to happen is you're going to have like x to the power of, say, 6 here. And then it'll say like x plus 2x to the third, plus, all these other things. All that's happening is this. Always look at what the base function is. I don't care what happens. If you can kind of go with me down this path. If I showed you something that did this and went, but then did that again. Look at where my arrows are at. They're both going up. Don't all these always go up? I don't care what's happening in between. I want to know what's happening on the outsides. And I can say, hey, you know what? I don't know what all this junk is doing in here because those are other functions being combined. And so it's making the graph do some other stuff. But because of both of these go up, I know that's going to be an even power. That's going to be x to the power of something. And I'm going to show you how to figure all that out. That's not as bad as what you think. Okay, we call that finding zeros. Okay, but for right now, you can go, man, I don't know what all that stuff is doing in the middle, but I do know that if I had to look at the base function, maybe like x to the power of 8, because both sides are going up, or it may be negative x, because remember a negative will just do what? Make it go down. Does that kind of help you out a little bit? Okay. Because I don't want y'all to get used to memorizing these and go, well, I never see those. Well, of course not. We're going to make things a little bit more messy, but it's always the messiness that happens in between. Look at what the base function looks like. Remember yesterday when we had that one function one that was doing all this stuff, and we said like, hey, f of negative 2, what is that? Oh, you go up to here. And I went, oh, this looks like a negative x to the 8th. I just counted how many times I went across the x-axis and went, okay, 8. It's a negative. That's it. So I kind of have an idea of the base function. I just don't know all the little math that goes on between it. That's actually really hard. Okay. Are you good with power functions right now? These. So if you see an even, what is your graph going to model? Even power. What are you going to model?
A parabola.
It's going to kind of look like a parabola. And as that power gets higher, as R gets greater, if you're just thinking of a base power, what's going to happen to like the little vertex? It's going to kind of flatten out a little bit, right? Well, what about even? What about an odd? Odd always starts out, when you have a 1, it's always just going to be a line. So if you can base it off that, when I have x to the power of 1, I know it makes a line. That means everything from there is going to kind of look like just a morphing of a line at that point. You're never going to have an x to the power of 3 looking like a parabola. It doesn't happen. Because remember, functions are shapes. They represent a shape. So a linear function will always create a line. Okay? A cubic function will always create this funky side S. Okay? Or backward side S. Whatever you want to think of it. Okay? As it goes up, that part right there, okay? This little section right here starts to kind of flatten out longer and longer and longer. Find the pattern. It'll make all this a lot easier. All right, well, how about this one? Power functions of the form a to x to the negative n. Remember, you have a rule for this. A to the negative n is equal to 1 over A to the n. Remember that? So you're looking at what? Fractions. Fractions with what on the bottom? A variable, which means, what are you going to have? A restriction. Why do you have restrictions? Because it's a variable and you can't divide by what? 0. Or anything that's going to create a 0. Look at the way these functions look. First off, look right here. Every single one of these right here. Notice what's happening to that line. It's getting closer and closer and closer to what? 0, but it's never doing what? Never touching. That is why whenever you try to do 1 divided by like 0, your calculator comes back and says domain error. It doesn't say syntax error. Syntax error means you try to use the subtraction key as a negative. Okay? No, domain error. It say, hey, you can't do this. There's no domain here at 0 because that's going to get infinitely close to 0 but never touch it. Okay? Now, notice 1 over x. Okay? For this one, I always remember odd powers are opposite. Okay? Notice this is 1 over x to the power of 1, right? There is a power of 1 right here, right? So I know it's always flipped. It always looks like this, okay? And then what's going to happen after that? As the power increases, these here, these little gaps, we will call these later. I'll go and give you the fancy word now. These are not called restrictions. That's called an asymptote. Okay. Same thing though. Restriction, asymptote means the same thing. Okay. It just gets a little wider. That gap gets a little bit further out. It doesn't mean that that line is going to not infinitely get closer eventually. It's just I'm starting it out with a little bit wider. Okay. I still think of this one the same way I thought with the lines. Okay. A line, because it's what? An odd power, right? Remember how the line still did that right there? Well, it still kind of goes down below. There's nothing just happening on top like it would a parabola. Either everything's happening on top or everything's happening on the bottom or whatever, you know what I mean? As their base functions. This one, I kind of think of that. It's kind of how I help myself remember that. Okay? I said, everybody's got their tricks to remember these. It's really up to you how you decide to do it. You know, and there's really I'm teaching you, but today I'm really kind of just showing you like, hey, look. Figure out how you're going to remember them. Okay? Well, if you can also have even powers. Even powers, everything's on top. Okay? Still, with that asymptote right here, that restriction, that just gets wider as the power gets higher. Two ways to remember these. One, memorize them. Two, test points. There's nothing in here that says you can't plug in points, right? Like even on this 1 to the x squared, I could start plugging in points left and right. Now you gotta be careful because it doesn't take long for this thing to get annoyingly small or annoyingly big. Okay? Like if you did to the power of 1, you're going to get a pretty good little answer. Like if you did a 1 for, I'm looking at this one here. If you did, like say you're doing a graph and you did like say, here's your x, here's your f of x here, and you did 1, well, that's going to be pretty nice. It's going to sit probably right around here, looking at this graph. Well, that's not a very good point. So you might be tempted to go, okay, well, let me go at the half point, like say 0.5, right? Well, the problem with that, if you do 0.5, you might end up with a pretty large number because that thing is going up. really, really fast. Okay, exponentially fast in the denominator. Okay, so you'd have to do 0.05 squared and then divide that by 1. You're going to get a really large number. Okay, or a really small, super small number. Okay, so just kind of be warned about that. Okay. Still though, you can kind of like at least give yourself some test points and go, oh, here's kind of what the graph looks like. It'll kind of give you some hints. Okay. Are we good so far? Like I said, I'm really just kind of showing you because like these are functions you're going to start dealing with all the time now. Okay, they're here to stay. Okay. Good. If you have a question about it, let me know. And if you see something go, why is it doing what it's doing? Ask me now. Okay. All right. How are functions of the form basically radical functions? Look at this one. These can be confused really quickly with power functions of just the normal like x, just because look at the little S shape you're getting. But like x, a cubic function, remember, I'm going to kind of draw it on here. A cubic function does this. Whereas a radical function does what? What it's showing. But can you look at something real quick here? And I did that for a reason. If I gave you this, now this is extending our definition of graphs a little bit, but if I gave you x to the power of 3, let me write that in black, I'm sorry. Now we know x to the power of 3 would look like this. Let me kind of draw it in red here. If it looked like this, right? More or less, right? I mean, just kind of the base function of it, that's what it looks like. Doesn't that look extremely close to the cube root of 3? Because that's what you're seeing right there, right? This function I just drew on is the function of the cube root of 3. Well, look at it. How do you get rid of a cube root of 3? How do you get rid of a power of 3? Cube root it and you go back to x. It's an inverse. That's why they look like that. You could literally flip that function and do this. Don't do that. You could flip it on its side and it's going to be the inverse of it. That's what we have as inverses. Lost the pen chip to this thing. I'm going to draw more. But do you get it? That makes sense on this one? So any one of these, and you'll see later on how to do inverses. Okay, we're going to start taking inverses of functions so you kind of see how they work. But that's really what they're doing is you're turning a function, it kind of just gets rid of it. Okay, but notice every single one of these, like I said, is based off what? If you look at all the odds, okay, well, a linear function has all real numbers, right? For a domain. Well, remember whenever we said, hey, cube roots or odd roots, what is their domain? All real numbers. And that's how that works over and over and over again. Well, anybody remember what a radical function looked like? Just a base radical. You did it. If you had me last semester, you took a assessment 3 and you had to graph a radical function, a square root function. Remember what that guy looked like? Remember just the hump? Okay. There it is right there. There was your base radical right here, right? Just this one right here. Just a square root. Look what happens as the index grows. That part just gets a little thicker there. So as the index goes up, what's going to happen to that little part there? It just, once again, like every other one, it just starts flattening out before it does its thing. Good. This graph also shows you why you have a restriction, why you cannot have a negative number, okay? Because look, your graph does not go into the negative range. Now, hear me, you're going to be graphing some that drop down, but that's where you have like a x squared minus 2 on the outside. So it drops it down a little bit. But the base function is a radical function, okay? Is everybody remembering the notation here? What they're doing? Remember those rational exponents? Watch out for both. You don't know exactly how they're going to give it to you. And remember, for sometimes it's nice to say the 6th root of x. Sometimes it's nice to see x to the 1/6 power. It depends on what math you're doing at the time. Okay. Are we good so far? Do you need a review? You're good? You're writing it down? The notes are going to be downloaded today as well, but still, you got to have these are on your midterm. Okay. I don't know which ones, because I don't know which one I'm going to give you for your midterm. So, but you got to know. Okay. Got to memorize them. Absolute value. Absolute value always has how many answers? 2, right? Okay. What's the absolute value? 0, though. 0. Because absolute value denotes what?
Distance from
0. Yeah. So how far are you away from 0 is 0? 0. How far are you away from 0 when you're at 1? 1. How about -1? Okay. How about 2? You have an idea of maybe what this graph looks like? By thinking that way, if it's always 0 and then it's 1 or -1, 2, -2. Yeah, V. Okay, so there is your absolute value function. Probably one of the more notable ones, but it's also one of the reasons, if you'll go back in time, I did say to you last semester, I said, hey, when you're graphing these parabolas, don't make it a V. Put that little hump in there, because if you start making it a V, you're going to get confused later on. And here's your reason why. Because you start creating the V, all of a sudden you start thinking parabolas are absolute values, and they're not. Okay? Now look at the notation of this function. That's a function. Okay? This is going to be something of the form. The absolute value is defined as this, where it says x if x is greater than or equal to 0. Okay, and then the negative part is going to be if x is less than. All that's saying is whenever you plug it, you got to give 2 answers. Okay. This type of graphing definition you'll see short is called a piecewise function. It's where we can say, hey, this graph behaves, this type of function behaves differently at different times. Okay. And this one does. Because I can't just plug in one number and just get this and it just work. I can't just say, hey, here's a cubic function, so I can just plug in 1. Well, 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Can't do that. This one's going to say, hey, there's some behaviors of this graph at 0, and there's some behaviors of this graph when things are positive. There's some behaviors at negative, and you're not going to always get the same number, and you don't. Right? You're going to get -1, a +1. So it depends on what you plug in. Okay. Like I said, one of the easier ones to understand. One that you're going to use now, and I'm going to show you this one. It's on your homework, and then I'm going to be honest. Bro, I've taken a lot of math classes, and I've never seen this. I've never used this one. So there you go. But it's here. Greatest integer function. And I think, okay, I'm lying to you. I think I did kind of use it in a like a really high level stat class one time to define some things. But it was like one of those things that we didn't really graph. We kind of just looked at it and went, okay, that works. And then we just kind of just moved on from there because it's weird. Master's level math class is weird because the professor kind of just hands you a book and goes, I'll test you later. And you're like, what's the homework? We'll figure it out. And you never know, it's never the same thing. So he kind of went, hey, does this look good to y'all? And he literally said, he goes, I don't know if this function works. You guys figure it out. And some of us said, yes, it did. Some of us said, no, it didn't. And then we were like, he's like, all right, y'all got an A. I was like, that's nice. Okay. How this one works, because you do have some homework problems. Okay, I'm going to kind of show you how it works. Notice it's still a function, right? And there's still some intervals in there. Okay. But this one denotes length and vertical separation. Okay, vertical separation is how far is this, from here to there. And notice it's consistent. Okay, I'm going to draw little lines here. Okay, that's your vertical separation. And then the length is obviously what? This. So this is what this is saying. F of x is equal to, okay, it kind of gives you like little double braces. Okay, and then we've got this right here. Notice they're giving you an x. Let me rewrite it. Let's do a vertical separation here. We're actually going to write this how we kind of would a slope. X over 1. And what would be my coefficient? 1. I don't really want to call it a coefficient. I'm going to call it a coefficient right now. It really wouldn't be the coefficient, but let's just go with that. So yeah, there's a 1 right here. Okay, so this right here is your length. That right there is your vertical separation. So notice that 1, that's saying, hey, you have a distance of 1 between these dots and these dots. Okay, well, how far are the dots apart? 1. Notice they just go over 1, there's that. They go up by 1, there's that. So if I gave you one that looked like this, and I will, let's say 4x cubed. Well, realize all this is saying is, hey, I have a dot here, and it's colored in, and it's going to go over, see, yeah, 1, 2, and 3. And then there's going to be that. And then it's going to go up here by what? Yeah, up here to the next one. Before the next one starts, you're going to have 1, 2, 3, and then there's the 4. That's all it's saying. So as that vertical gets higher than 1, or even less than, you're just going to see those dots doing this. Go further and further and further apart. And as the inside one gets larger, it's just going to do this. Okay? If it got smaller, now it can also get smaller. They can get closer and closer and closer and closer and closer together, obviously. Right? So, but that's how that one works. You get done with it on this homework, you'll probably never see it again. It's not, I don't believe it's on your midterm. Okay? If it is, the reason it probably isn't is I'm not going to make you graph that. Okay? Because it's, look how annoying that is to graph. Okay? And time-wise, that would just be really mean to say, hey, you got an hour and 15 minutes to graph this, and that thing would take like 15 minutes alone just to graph, so that wouldn't be very right. So. We good with that one? Okay. Piecewise function. These you will see a lot. A big hole developed for me in this class when I took this class long time ago is the professor skimmed by piecewise functions. Great professor, but we just skimmed right by it. We didn't really hang out on it very long. I'm not going to hang out very long either, but I do want to kind of like point it out. Like I said, a piecewise function is literally what it's doing. It's taking pieces of functions and putting them together. Okay? Look at this, and it says f of x is equal to, well, look at this very carefully. Kind of get this a little smaller here. Look at this part here. What is this right here? What kind of function is that? Just that part. Don't worry about the whole thing. Worry about that little section.
Mm-hmm.
Yeah, that's a linear function. So it's saying at some point on this function, this guy is linear. But then he switches and he turns into a what? A parabola, exactly. Okay, now look at it. It actually tells you when. If you think of a piecewise function as just some guy giving you direction going, hey man, go that direction straight down that road, right? But then you're going to take the loop, curve, to the right. He's giving you two separate directions, but he's saying, for right now, from here to there, you're going to go straight. That's exactly what this function is saying. He's saying, hey, if x is less than or equal to -1, right here. Anything less than that, man, you're going to have a straight line. And there's the graph of it right here. But anything greater than 1, or -1, sorry, what are you going to start having? This parabola. Okay. This right here, do you notice how this is an open circle here? This is a closed circle? That open circle, you can write this down. You're going to learn it later on, but it's very good to go and learn things now. Remember whenever I showed you that line where things like never were going to touch? We called that a restriction. The reason I don't want you to hold on to that definition completely is because the reason we're calling it an asymptote now, while that is still a restriction, well, this is also a restricted value. You can't have -1 twice. I can't tell you, hey, go straight and turn. That makes literally no sense, and you should have me committed. How are you going to go straight and turn at the same time? That's what you're doing right there. You try to make both of those a filled-in dot. Okay, that wouldn't be a piecewise function. That is two totally separate functions doing their own thing. This right here is called a removable discontinuity. That's all that is. I went in there and removed something. You'll also see that in functions like a straight line where you'll see like a little hole in there somewhere. But we'll call that a removable discontinuity. So when you have to graph one of these, just look at the behavior of it, okay? When it's from here to here, do this. When it's from here to here, do this. There's one on your homework, we'll work through it, okay? And it's literally, it's pretty simple. You just look at what the thing says. If I'm within this range here, I use this. If I'm within this range here, do that. Okay? Good thing is you want to graph these, you'll just have to tell me the behavior of them. Like, what is the value of this number, okay, in this function? So notice if I gave you this, what is f of 3 of this whole function here? Well, does that mean I plug in a 3 everywhere? Nope. Look at what f of 3 says. It says, hey, I'm giving you 3. Which one am I going to use?
The parabola.
Yeah, I'm using the parabola right here. Because 3 is greater than -1. And so I'm only going to be graphing there. That's the one you would plug in at. Okay, but if I gave you f of, say, -5, now what am I going to use?
Linear.
The linear. That can help you out a little bit, kind of see how they work now. You're just saying, you give me a number, which one says to do it, okay? Okay. Even if I gave you this, let's just go ahead and make it, let's throw a little, make it a little bit harder. What if I said f of -1?
Linear?
Linear, why?
Because this is equal to.
Yeah, the or equal to symbol. Because that's where I'm allowed to use it at. Right there, or equal to. Couldn't use it on the parabola because the parabola does not contain the or equal to. Okay, can I help you out with those piecewise functions now?
So that f of 3, where would that point be?
F of 3 would have gone right over here. It would have gone way over here and way up. Remember, because you just said 3 up, somewhere up there. So you would have put it right in here. And you just put 3 in there, so it would have been a 9. Because 3 squared is 9. Does that help you out? Okay. Well, let's try some out here. Let's do some homework examples. Tell me, step 1 of 2, identify the general, hence general shape of the graph of this function. We're gonna number here. Let's go 1, 2, 3, 4. Raise your hand for number 1. Is it an absolute value?
No.
So we can get rid of 1 and 2 automatically, right? Raise your hand for 3. Raise your hand for 4. Ooh, half and half. Well, guess what? The linear. Okay, look at how it's written. Okay, first off, remember what you're seeing up here. Let me show you mathematically. You're seeing negative to the 7/8 times x to the power of 1. That x is not in the denominator. And so therefore, you don't have any sort of weird things happening right now. You could really rewrite this as, remember this, you have f of x is equal to a to the xr. Notice this right here, that's my a. My x is that guy, and my r is just a 1. You have a linear function. Okay? And that's your base function. Now you go, okay, hey, I found out it's a linear. Okay. Step 2 says what? Let me kind of blow that up so you can see a little bit better. Find 2 points on the graph of this function other than the origin, which means you cannot use 0, 0. They're not stupid. Okay? That fit within a negative 10 by 10 and negative 10 by 10 grid. It's going to be the same rules on your midterm when you graph for me. Make sure all your points are contained within my graph. Do not start drawing outside my graph. Okay? Express each coordinate as an integer or simplified fraction or round to 4 decimal places as necessary. Find me some points. Try to work it out with us. Find some points, and then I'll give you my points. Remember that you cannot use 0, 0. Because that would be kind of a cheat. Everything on these base functions have a 0, 0 in some weird way. Right now. Base functions anyway. Can you use your calculator?
Yeah.
Why can't you use your calculator? Remember I showed you how to do fractions on your calculator. So if you need to, use your calculator. I don't know if you gave me the right number, don't worry. Okay. On your midterm, I have everything calculated pretty much. And if not, I'm pretty fast at the calculator, so. Let's do 1. I'll do 1 real fast. X. Then I've got f of x. How about 8? I wonder why I'm going to use 8.
Well,
Because look, whenever I do f of 8, I get negative 7 over 8 times 8 over 1. Those guys cancel out. And I'm just left with a negative 7. Problem is you can't go much higher than that. Okay, because I can graph 8, negative 7. I actually messed up on Haas because I don't read instructions very well sometimes, and I put, hey, 16 will work really nice. Well, yeah, it does. It works great, but it's not graphable on that graph. Okay, so I came here and I used 4. So f of 4 is equal to negative 7 over 8 again, times 4 over 1. That goes to a 1, that goes to a 2. That gives me negative 7 over 2, here, negative 7 over 2, which just turns into negative 3.5. And there's 2 points. You okay with that one? Yeah. I need to go real quick here. Let's look at another one. Now, can you see that one? No. How about this nice little piecewise function here? Let's worry about the first one real quick. Notice it says evaluate. Not saying graph. It's just saying evaluate. But can we do something real quick to maybe help y'all out a little bit? First off, this piecewise function, remember a piecewise function is a combining of functions. It's saying this function, you get this function from here to here, you get this other function from here to here. And don't start thinking that you just have to have 2. You can have piecewise functions that have up to 10 and more. And you see these a lot in statistics. Not the statistics class you'll be taking with us. I really wish I could teach you that, but it actually takes a little bit of calculus. Not a lot, but a little bit of calculus to come up with these. But you see this a lot with probabilities. It'll say something like, hey, what's the probability of this happening in this area, then this happening in this area, then this happening in this area. And so they put it together as a piecewise function. Okay. You will see stuff like this in statistics if you see it, but I don't make you create the function. But there is 2 functions. What are they? What's the first one? The 2/3 x minus 5.
Linear.
Exactly. Why is it linear?
The first degree.
The first degree. There you go. Okay, what's the second one?
Linear.
Exactly. So you have 2 linears. It's just from here to here, it's going to do this, and from here to here, it's going to do this. Okay. I don't know what it looks like. We could graph it. We could go into Desmos. Should you probably go into Desmos and check these out sometimes? Yeah. The more your eyes get used to seeing graphs, the more they're not going to freak you out. Okay. So let's do the first here. Evaluate x at -3. So which one am I going to be using? The top one or the bottom one? The bottom. Because look, it says when x is greater than or equal to -5. -3 is greater than -5. Okay. Can I say it this way? If you owe me $5, what would you rather owe me? $5 or $3? Okay, so 5 is less, -5 is less than 3. So plug it in and then you just do the math. So you're going to have this 1/4 times -3 over 1 minus 6. That's going to be -3 over 4 minus 6. Or -3 over 4 minus 6 over 1 times 4 on both equals -3 over 4 minus 24 over 4, which is going to give me -27 over 4, and there's your answer. Or, if you'll permit me, and for those of you who didn't get to see this, remember, if you're using, as I told one of my fellow math teachers yesterday, she asked me, hey, how much fraction do you make your college algebra students do? I go, well, hopefully none, if they pay attention to me. And she went, what? I go, man, since Dev 1, these students have been doing fractions. I go, they did fractions in Dev 1, Dev 2, and intermediate. I go, if they failed this class because of fractions, they deserve it. So let's do this on your calculator real fast. Remember, if you haven't seen this, I'll do it for you real quick. If you haven't seen it completely, go back and look at the video. I do not know your calculator, just FYI, okay? I'm going to be using my calculator, which is the TI-30XS, okay? All right, there, perfect. So notice for this one, using this piecewise function, I can do it this way. You can literally write it this way. Come in here, knock everything out. So I have a fraction here. First off, you're gonna wanna go to mode, make sure that thing is in math print. Okay. Get out of that. So my first thing I'm gonna write down is gonna be my fraction. So what do I have here? Is it 1/4?
Yes.
1/4, and then what were we plugging in? Is it -3? Yes, -3. And then plus what? Oh, -6?
Yes.
Oh, there you go. That took all but 2 seconds. Okay, so try to do that. Try to remember to do that if you can. If you want to work out the fractions and you're really good at them, have at it. But don't let it be a stumbling block for you. Okay? Are we good with that? Okay. So if you see on some of your notes sometimes where it looks like I just put the answer down, I didn't work the fraction, you know why now. Okay? Let's come back. Work for me the second one then. Tell me, evaluate this function where x is equal to -5. Top function or bottom function? Bottom, exactly, very good. How do you know to use the bottom? What's the telltale sign on that one?
Equal to.
The equal sign, look for that, or equal to. Come in here, I'm gonna have f of -5 is going to equal 1/4 once again times -5 all over 1 minus 6. You can do the math to that, but you should have got -41/6. Want to check it? Always check. Like I said, my math can be wrong sometimes. You always check my math. Let's come in here. Once again, I've got 1/4, parentheses, -5 minus 6. Oh, 29/4. Oh, wait a minute. Hold on. Nope, it's wrong. Yeah, I did wrong on that one. See, use your calculator. Did you get 29/4?
Yeah.
You know, it's good. Is the only way you're gonna know I got that wrong is I'm gonna keep this in the video because I'm a nice guy. But your notes will not have the wrong answer. Okay, so that is wrong, -29/4. How about the next one? Evaluate this function at -9. And what are we gonna get? Which one am I using? Top or bottom?
Top.
If x is less than -5, remember -9 is less than -5, okay? Well, it's less than, so I gotta come here and start putting everything in my calculator, and I'm gonna get 2/3. Times -9. Minus 5. Hot dog, my notes were right. How about -11? And there it is on the calculator up there, so you can see it. That, fraction button is a lot more powerful than you realize. It will even do quadratic formulas. Okay, you can put the whole quadratic, you can't put the plus or minus in there, unfortunately. But like your vertex form, it'll do that. Okay, it does everything. Okay, anything you can put in a fraction. What I need you to start being very careful about though, is watch out for the parentheses. Okay, because if a lot of stuff is happening in your denominator, you still need to go ahead and put parentheses down just in case. Okay, it's better to go ahead and wrap your numerator in parentheses. Okay, if you have a lot of stuff happening up there. Okay, let that better be a better safe than sorry kind of thing to get used to. How about this one here? What do we have? Identify the general shape. You have u of x is equal to 7 over 6 x to the power of 3. First off, tell me this. What is the base function that we are looking at?
A cube. Three.
Where's your x?
The denominator.
Right. You can't pull that x out and put it out front. Okay? If I had 7x all over 6, that's the same thing as saying 7 over 6x. Okay? I cannot do that with this one. So notice what you're seeing here is 7 over 6 times 1 over x cubed. So now what are you seeing? Look for the one that looks like this. A to the x to the negative n. Yes, scroll back up, take a look. Right there. You know what's going to help you on those? Do you have an x in the denominator? Which means you have a variable in the denominator, which means you have a restriction. So that should kind of help narrow it down to which ones it is. Now you just got to decide at that point, is it even or odd? Right? So your graph is going to be this one right here. Go and scroll all the way back down. Your graph is that one there. Okay. This one would have been what? It'd have been even, right? It'd been like x squared. Okay, what's this one?
The cube root.
Cube root, exactly. How about this one? A radical, right? But what kind of radical? It's probably got a what on the outside of it?
Negative.
A negative. That's what flipped it across that x-axis. I want you guys to start kind of, you're gonna learn all about that, okay, about that flipping and moving and stuff like that. But if you can kind of start seeing it now, man, it makes 4-1 so much easier. Okay. Find me some points.
Here's the equation again.
Sure can. Here, I'll write it down. You have u of x is equal to 7 over 6x cubed. See a lot of people doing hand math. Go back to my syllabus. This calculator right here, I have a link on Amazon. I am not affiliate. That'd be illegal. I'll get arrested. It's like $11. Okay. And I'll let you use one of these. If you can learn how to use one of these now, I'll let you use one on the midterm. I'll give it to you. Not give, you got it back. Still. And yours may, look at yours very carefully. You might do some Googling on yours. If you tried, you're like, oh. Come in here, notice I'm gonna have, once again, I'm gonna say that we have 7, 6. How about 1? 1's always a nice one. And then I'm going to hit that and put a cube. Look at that. Take it out, hit enter. Now that's okay. But remember right here, if you hit this little button here, you still gotta graph that guy. And that's 1 to the 1/6 or 1.1666. So basically, if you had to graph that, you're gonna put that as close as you can to the 1, right? Okay, well, let's do another one. How about 4? Okay. Once again, let's come over here and I'll hit my fraction. I've got a 7 on top, I got a 6. With that cube, to be honest, I still want you to be careful. Let me do something real quick. In fact, I'm gonna change things up just real quickly here. It really doesn't matter if your power is a cube. Okay? Because if I said -2 cubed, you're gonna end up with a negative, right? Because a negative and a negative make a positive times a negative, you're okay. But if you have an even power and you're gonna plug in a negative number, remember to wrap that negative in a parenthesis before you raise it to that power. Put the power on the outside, or you're gonna get a wrong answer. Okay. I'll show you after I do this one. Let me just kind of do this. Let's do 4. Remember the little hat button there? Hit cubed, hit enter. Syntax or what? Not like that. Oh, I see what it did. Got to be careful. It put my parenthesis on top. So hit delete, move it out, then hit my parenthesis. Okay. And there's my answer. Notice what happened with that one though. Might have hit 4, but what happened? That's a really small decimal, right? Then I said, well, it makes sense that that's happening because why? Well, look at what's happening at 4. If we kind of had a generic 4 over here, look at where that line is at. It's getting super, super close to that line, but what's it never going to do? Touch it. It's never going to touch it there. It's never going to touch it on the y-axis, and it's never going to touch it on the x-axis either. Okay? Because even with this one, while we're concerned with the the y-axis, because you can't divide by 0, look at what's happening on the y-axis as well. There's another restriction there because you can't even put an x in there. Okay? Because if you put x in there, you're getting x cubed. You're still going to get that 0 on the bottom. Okay? So you got to be real careful. So the range is going to look a little weird too. Remember how you got those the union graphs for some of your domains? You're going to have a union graph as well on your domain. Okay, sorry. You're going to have a union with your domain and a union with your range. Okay, all starting at 0. Okay. So notice you got 2 little things here. Now, very quickly, just so I can prove it to you again, and then we'll call it a day today. -2 squared should be what?
4.
4, right? Look what that calculator just gave me. Okay? That's wrong. That's completely wrong. I'm going to do this one last time. I'll do it on these notes right here. When you see -4, what you're actually, I'm going to put this way. Let's say when you see -2 squared, what you're actually seeing, what your calculator sees is this. -1 times 2 squared. It squares the 2, multiplied it by a negative. That's why you're getting that -4. When you're replacing, you have to do this. -2 squared because PEMDAS. Now that's -1 times 2 squared. Well, remember now that's going to here, and you end up having 1 times 4. Or if you don't remember all that, wrap your negatives in parentheses. Okay, so you get the right answer. Okay, come in here and do this. Outside, and notice you get the 4. Okay, you only have to do that when you have a variable and you're going to put like a negative in for that variable. Just get used to putting a parenthesis around it. I don't care what you're doing, even if there's no powers involved. If you go ahead and just get into the muscle memory of just wrapping that bad boy in parentheses, you're never going to have to worry about it later. But if you decide to start picking and choosing when you're going to do it, you're going to pick wrong eventually. Okay? And it's usually that eventually is gonna happen on a midterm or a final. Okay? So it's better just to be in the muscle memory of doing it. I tend to just wrap everything, which got me in trouble in calculus a lot. Okay, not mathematically, it just really annoyed the professor. He's like, why are you wrapping everything? I'm like, I'm not messing up signs. But still, okay, to help you out? All right.